So just to finish off this look at integration, using symmetry and ideas to make life easier for ourselves. So if we have an even function, well, we know that function negative x is function x, and we've seen this before too. So it means I could, instead of integrating from minus a to a, because of the symmetry, I could go twice naught to a. We could extend that idea. Now, it'd be very rare, but if it does happen, we can use it to our advantage. If we notice we have an even function that has been shifted horizontally, say, and then the symmetry is around that point of shift. So say we've moved the whole curve to x equals c, but then we're integrating from c minus some amount to c plus some amount. Well, we could use that idea there and go twice from c to c plus a. Is that going to save us a lot of time? Possibly not. Where it might be useful though is odd functions. Remember, function minus x is minus function x. And remember, with the symmetry on that one, the integral becomes 0. So it could save us time if we notice the horizontal shift on the odd function. Because if you've got symmetry c minus a to c plus a, then well, that's going to be 0, because of the symmetry about whatever point we've moved it to. So, yeah, it's a rare that it might happen, but it's an idea. This one is very useful. If you integrate from naught to a of function x, you'll get exactly the same answer if you integrate from naught to a of function a minus x. Very easy to prove via a simple substitution. I'll let u equal a minus x, so du is minus dx. Change the limits, and basically the limits end up swapping around. This becomes my integral then. But it's a definite integral. Swap the limits around, make it positive. It's a definite integral, so I could use any pronumeral I like. So function x dx, and there's the proof that they are the same thing. So if you are using symmetry, keep in mind, odd function times odd will be even, odd times even will be odd, even times even is even. So basically, the same type of function multiplied together will give you an even function. The different ones will give you odd functions. The sine cubed, but we see the symmetry, minus 1 to 1. So sine cubed, well hang on, that's an odd function, because we're going to go odd times odd, which is even, and then we multiply it by odd again. Well, even times odd would then give you odd. Odd function, don't waste time using your techniques to integrate sine cubed. We know that's 0. Here's where that last one is useful, because to integrate that is a bit tricky. But if I change it to that, it's a heck of a lot easier. So I can always replace it with, in this case, 1 minus x. Wherever I see x, I change it to 1 minus x and vice versa. Put it in index form, a very, very simple integral. Add 1 to the power over the power, substitute in, and we have our answer. Certainly a lot easier than trying to integrate the initial function, because we can't create derivative times function there and all sorts of problems. A word about what we call improper integrals. So what is an improper integral? Where the boundary is undefined somewhere. Technically we should be using limits if a solution exists. It may well be there is no solution. Something like this. Here's our hyperbola, and they're saying integrate from 0 to 1, but hang on, it doesn't exist at 0. So if you think about it, hang on, I'm trying to find the area under a curve and it goes up to infinity. That's crazy. So we can investigate using limits. So we say, well, we know we can't substitute 0 into this function. So let's see what happens as n, I'll just replace it with n for number. As n approaches 0, what's happening with this function? And if we integrate, I get log x. So subbing in, it becomes minus log n, but again, log of 0 doesn't exist. So in this case, no, there is not an answer to that. That one is undefined. It won't work. As opposed to something like this, because of course you can't substitute infinity in there. So 1 to infinity of this, well, let's make it a limit. We'll do 1 to n, and let's see what happens, the limit of the answer. X e to the minus x squared, it's in the form derivative times function. So I get minus a half e to the minus x squared. Substituting in, I can now do this limit, because it's e to the power of a negative number, because minus n squared will always be negative anyway. Backwards exponential, I know as n approaches infinity, that's going to 0. So in this case, I can get an answer. So that limit does exist. And this idea about area and inequalities, if the curves go in that order, well, if you find the area under them, then the areas have got to go in that order as well. Here's an HSC question. So 2009, we have our, speaking of y equals 1 on x, there it is, that's the one they used. And they've drawn up a rectangle, inner and outer, to give us a bit of an idea of how to do this. They want us to show this inequality. Okay, so I'm going to use that idea. Area of the inner rectangle will be less than the area under the curve, which will be less than the area of the outer rectangle. That's the idea we're using. So let's sub it in. Find the area of the inner rectangle, 1 on n. Area of the outer rectangle, 1 on n minus 1. And in between we get that integral. So I'll integrate log x, but not quite what they want me to prove. So I'll play around with a bit, because I'm going to multiply everything by n, because looking at what we want to prove, there was that fraction with n on it, so it looks like I need that. And now I'm going to bring the n into the log. That gets me now the n on n minus 1 to the power of n. Now I'm using that idea when I say about the continually increasing function. So e to the power of x is continually increasing, so they will be preserved. So e to the power of 1 will be less than the n on n minus 1 to the power of n, less than e to the power of n on n minus 1. Turn everything upside down, so the inequality signs change, because when you flip, you change the inequality sign. And rewriting that, we basically have what we want. We have Old Cambridge, there's some questions from there. New Cambridge, there's some questions there. And then there is the 100. Now it would be very mean to make you do a 100, so you don't have to do number 78. Okay?